Good afternoon, everybody, and we're looking at the contents. We're going to talk about the overview and introduction about what we're doing, what we're going to talk about, and then going to look at some basics of CT. So if you're not familiar with CT, I'm going to give you a little educational overview what the technology is about and how do we create the results, and then also show you some 3D visualization examples and what you can do with the software to look at data sets. And I also have some examples that we scanned and share that with you, and also very specific software tool that's available for fiber orientation analysis. So we're talking about composites materials that can be found today in aerospace, and you see a picture on the right of a Boeing Dreamliner 787, and you can see it's a lot of composites in there, and seems to be the new trend in aerospace, but also in automotive industry, especially with the all-electrical vehicles. But also we see this technology being used in other things like you see a snowboard, tennis racket, and a bicycle, stuff like that. You see a lot of components made of composite materials. So this is a list of common problems, defects in composites. So a lot of times we see porosity being of interest, to see where the porosity is. It's critical. The technology here will help you to identify those. Foreign materials in the process, sometimes foreign materials can be caught into the composites and be part of a component, and it's not, or it maybe influence the integrity of the part. Bonding defects is a very common problem, and the alignment of fibers, the alignment or misalignment of different plies is something that could potentially happen. Fibers, so if it's not in the process, it's not put down correctly. Cracking, delamination, so that's when you have different layers separating in the process, and you see air or other material between two fibers or plies, for example. And then also, in some cases, fiber defects. In general, testing of composites can be divided by, destructive testing and non-destructive testing. So where destructive testing is typically like stress test, fatigue test, micro-sectioning test, so we cut it and look at it, what is there. And then there's the non-destructive testing. Eddy current is one technology that's being used to do non-destructive testing, ultrasonic, chirography, and there are some others, but we're going to focus on X-rays only. And under X-rays, we have digital radioscopy. We talk about that in a little bit in this presentation. Then there's also laminography, which is used in the composites environment, non-destructive testing, and then there's computer tomography, and this is our main focus. But I'm going to show you what we can do with digital radioscopy at first. So basically what it is, you see this picture here on the right, you see a typical manipulator. The X-ray tube is on the right-hand side, the detector is on the left-hand side. This picture, and typically what you want to do is you want to move up or down and left and right, and you want to tilt and have different views through your component in order to see potential defects. Here you see an example. This is a bicycle frame, and this is a digital radioscopy image of that section where the wheel connects to the frame, and you can see some of the wrinkles in there, and you can see some stuff that might be of interest for you. And also, this is another example, in another area of the frame, and you can see this is a static image, and the third picture I have for this is the hub area, where it also shows the different components, like the steel parts, and there's a screw in there, and you can see some wrinkles, you can see some lighter areas where you have potentially porosity or debonding. And in a lot of cases, this is just enough to see what you want to see. And then we can also enhance the image, the digital radioscopy image, by applying filters. And you see a static image here that can, make things visible to you in a static way. But we also, and that's what we call HDR, is a filter that can be applied in live. So on this screen, you can see that will be a live image of, in this case, a bicycle fork, and you can see how we apply. On the right-hand side, you see the applied filter. On the left-hand side, you see the raw image from the detector. And so with this motion, it gives you a good idea where the defects could potentially be, but it's still not a 3D 3D image. It's just a 2D image in motion. And then there's laminography. That's a technology where you have your sample in the middle and you rotate the tube and the detector around the object, and you take different shots from different angles, and the software would then stitch it to, or put it together and reconstruct a slice through a certain or special area. So this is used when you have large parts and you want to look inside and have a better or more information about the depth of the defect. So now we're going to talk about the main subject, which is computer tomography, and I'm going to show you very briefly the basics of computer tomography. So the building blocks of a CT system consist of the source, the X-ray source. In this case, you see two tubes, a microfocus tube on the top, and below that is a what we call mini focus tube. So different power sources, so you can penetrate more with a more powerful tube, and you can see more details with a microfocus tube. And on the right, you see, in this case, two detectors. A lot of systems only have one detector and one tube. In this case, this is our CT modular, which can be equipped with two detectors and two sources. So you see a flat panel detector on the right, on the top right, and then a line detector below that. And we have a rotary stage. That's where the sample has to be attached to. And we have a manipulator. In this case, it's a granite-based manipulator for accuracy purposes, but it can be made of other material, steel or aluminum, if the accuracy is not a high demand. Then you typically have an X-ray cabinet or a vault or some sort of X-ray protection and a control unit. So the principle, what we do is we have an X-ray source. You see that here on the left-hand side, and on the right you see a detector, and then in the middle is the rotary stage. And we rotate the part typically 360 degrees or less, and we acquire 2D images from different views of the part. After that, after we acquired all the images, we will put that through an algorithm, and very often, it's not, I mean, there's other technology out there, but very often we do filtered back projection, which gives you a virtual slice through the part. And see here we have an example of a cylinder head with 3 slices, but this is of course at the end a full volume of the entire part, and you see the reconstructed volume would then be represented as a 3D volume, and every pixel in this volume is what we call a voxel, volume pixel. So that's an artificial word for the pixel in the volume. So with that data set, let's see, show you this video. So this is how it works. So you can see there's the projection on the left-hand side, and as we rotate, this is about maybe 45 degrees, you can see if you overlay all the projections by the software, as further you scan or you rotate, the clearer the image gets. And if you have a full rotation, in this case 180 degrees, you see a full reconstructed virtual slice through the object. In this case is a medical example. You see a human body, you see the spine in the middle and probably part of the lung on the lower right-hand side. But this is how it works. So the next question is, how do we position the part in the field of view? In one case, you have it very close. If you have a large part, you have it close to the detector. Or another case, if you want to magnify more, if you want to see more detail, you move the part closer to the tube. But as you can see, you lose field of view. So you can only scan smaller parts, or you only see a part of the whole sample, but you have a higher resolution. That comes to the subject's resolution. It is determined mainly by the number of detector pixels. You can see that on the left. So in this case, for example, you have 200 microns by 200 microns pixel size on the detector. You have a sample that has a given diameter. Let's say we have a 30 millimeter sample that fits in a 30 millimeter cylinder. The voxel size would be, if you have a 2000 by 2000 detector, you would also reconstruct, the volume would be 2000 by 2000 by 2000. The voxel size would be about 15 microns. And you can do the math yourself. If you have a 2000 by 2000 detector and you have a sample that's twice as big, 600 millimeter in diameter, you would have about 30 micron voxel size. or the other direction, if you only have 15 millimeter diameter, you would have a voxel size of 7 to 8 microns. Another way of reconstructing and scanning samples is what we call a helical scan. So instead of have the vertical axis sitting still while you're rotating 360 degrees, you would rotate and move up at the same time or down, and the images you catch would be described on a helical, or some people call it spiral path. And so with that, you can generate data sets that are in high resolution, but they are just bigger than the field of view in the vertical direction. So you can scan something that's larger, and you have a single data set with no need of merging, or you wouldn't see any joints or overlap or something like that. So, and also at the same time, it also eliminates some of the artifacts we typically see in some of the regular cone beam CT. So in this case, this is a stack of CDs. You can see on the left, this is a regular CT, and see in the middle, it's pretty sharp, and as you go further up in the beam, you will see some, unsharpness, or you would lose the resolution in this direction. And with the helical CT, you're going to keep pretty steady, stable resolution across the whole scan field. So now we're looking at the data set itself. So now we have generated a data set consists of millions of voxels, and now we can use software to look at the voxels. So on the upper left, you see a cross-section through the data set in the direction of the scan of the turntable. On the right, you see another cross-section that's in the other direction, and also in the vertical plane, you see a cross-section on the lower left. And then you can also, the software can also display three-dimensional views of it. So this is what you see on the lower right. It's a virtually cut open 3D set. So that's a simple way of showing things or looking at stuff. Typically what you want to do, you want to align your data set. For in this case, you can rotate, you can grab the red arrows and move the view left and right in order to have, or up and down, you can rotate it in order to have an orthogonal cross-section view through the data set. Another way of looking at it is if you identify areas, flat areas, you can identify a plane like you see on the upper left corner. It's a straight flat area. And if you want to look at this area only, you can identify that area and align the data set to that plane. And then you see on the four windows on the upper left show a cross-section parallel to that plane. And then you can go through the data set and look through in parallel to that data set. Then there's an unroll function. So if you have, in this case, this is the hub area of the bicycle, you can identify a cylinder, and you can then unroll that cylinder. And as you can see on the main screen, this is 3.49 millimeters inside the center cylinder. So we're looking at exactly 3.9 millimeters from that surface inside, and what it shows you is, delaminations and porosity and all kinds of stuff in that area. And the software is interactive, so you can scroll through back and forth, and you can see where you're at, and you can go to certain areas too. You can jump to exactly 2.0 millimeters if you want to, or somewhere where you want to look at where you know it's critical. Another very nice feature is the height marks. So what you identify is a surface that can be odd shaped in any way, and it will then, and this is typically what you do with composites, or very often it's not a flat straight part, but it has and that's the beauty of composites. You can create all kinds of shapes, and as you can see here with the height mark, you would be parallel to that surface. And now you can see even the plies and the fabric or the fibers where they show up in this exact plane. Yeah, from that height mark plane, 1.81 millimeter from the surface down. So I have a few examples here. This is a section of a helicopter blade, and you can see a lot of porosity inside here, and you see also the fibers. And on the lower left, you can also see that there's a ply that we are sectioning in this view. And this is a new materials. Now a lot of people trying to combine aluminum with composites and stuff like that. So this is a sample that we scanned, and it has two aluminum plates. In the middle is the fiber section, where we can then reconstruct the three-dimensional view of it, and you can see it was clamped in a bracket. Scan it, and then you can see inside. You can see the fibers. You can see the porosity of the resin and how it was bonded between the two aluminum plates. You see porosity even inside the aluminum plates, and this is another example where you can see inside what's going on in this video. I hope it comes up. So you can also create videos like this with the software and go through and browse through the different layers and identify porosity or cracks or whatever you want to look at. Another example for a bicycle frame where it uses automatic wall thickness analysis. So what the software does, it tries to identify a range of wall thicknesses, and it will color code different wall thicknesses depending on the wall thickness. So on the lower right, you can see there's an area that's a lot thinner than the rest of it. So you can see very nice and easy without manual measurement where potential problems are, where we can use, or we have to change the process in order to fix that if that is a critical thing. We also we talked about fiber orientation. So now we have a data set that shows us the fibers, and we can visually see them typically, or in some cases, not in all cases. The software is able to identify the fibers or the orientation of the fibers. It doesn't need to identify every single tiny little fiber in order to do that, but it has to find a gradient in the 2D image or in the cross section in order to see the direction in a specific location. And then it can color code the fibers or the areas depending on the orientation. So you have a history. You can also apply different colors to different angles. So, and this is the 3D orientation. So you can do that on this little planet here. You can grab this little dot on the right-hand side, and you can move that around, and you can define a different color for a certain angle. Or in the cross-section, you can see by color what's the orientation in that specific region is, and it also allows you to display vectors, and those vectors can be shown and can be adjusted and set up in different lengths and different colors and stuff like that. So that's, and a lot of times this is very useful tool. So this is another view of it. On the upper left, you see, just a black and white CT scan cross-section. So with the fiber orientation, you can see at a glance the different angles. So that's a pretty useful tool. And that is the end of my presentation.